Temperature is one of the important variables in any industrial process. Le Chatelier's principle can be used to predict the effect of temperature on the equilibrium of a reaction. You have learned that whenever a system at equilibrium is subjected to change in concentration or pressure, the reaction quotient QC no longer remains equal to the equilibrium constant Kc. However, when a system at equilibrium is subjected to change in temperature, the value of equilibrium constant Kc itself changes. For example, the equilibrium constant for the gas phase reaction of the formation of ammonia from nitrogen and hydrogen at 298 Kelvin is 6.8 multiplied by 10 to the power of 5, while it is 41 at a temperature of 400 Kelvin. The value of the equilibrium constant for a given reaction varies with temperature. In general, equilibria in which the forward reaction is exothermic, that is, where the enthalpy change is negative, have equilibrium constants that decrease with an increase in temperature. For example, the gas phase reduction of nitrogen and hydrogen combining to give ammonia. In this reaction, the forward reaction, that is, the formation of ammonia, is an exothermic reaction, and the backward reaction of ammonia dissociating into nitrogen and hydrogen is an endothermic reaction. According to Le Chatelier's principle, raising the temperature shifts the equilibrium in the direction in which the heat is absorbed. It implies that endothermic reaction is favored. So, ammonia absorbs the heat to dissociate into nitrogen and hydrogen. Hence, on increasing the temperature, the rate of backward reaction increases, or the rate constant for backward reaction, Kb, increases. You have also seen that equilibrium constant Kc is equal to Kf divided by Kb, where Kf and Kb are rate constants for forward and backward reactions respectively. As Kb increases in the denominator, the value of Kc decreases. Thus, for an exothermic reaction, the value of the equilibrium constant decreases with an increase in temperature. Equilibria in which the forward reaction is endothermic, that is, where the enthalpy change is positive, have equilibrium constants that increase with an increase in temperature. Consider the gas phase reaction of the decomposition of phosphorus pentachloride into phosphorus trichloride and chlorine. The positive enthalpy change for this reaction indicates the endothermic nature of the forward reaction. If the temperature for this reaction is raised, then the forward reaction of PCl5 dissociating into PCl3 and Cl2 occurs. As the rate of forward reaction increases, the rate constant for the forward reaction, Kf, and consequently, the value of equilibrium constant Kc also increases. Thus, for an endothermic reaction, with an increase in temperature, the value of equilibrium constant Kc also increases. The effect of temperature on equilibrium can be demonstrated using nitrogen dioxide gas. Nitrogen dioxide gas, which is brown in color, dimerizes into colorless dinitrogen tetraoxide. This dimerization as you can see from the value of delta H, is exothermic in nature. The three identical sealed tubes that you see here contain nitrogen dioxide in equilibrium with dinitrogen tetraoxide. As you can see, all the three tubes contain the same amounts of NO2 and N2O4 and have the same brown appearance. Now, out of the three sealed tubes, one is placed in a freezing mixture, one in hot water, and one is left at room temperature. What do you observe? You can see that the tube placed in a freezing mixture has turned pale, while the one placed in hot water has turned dark brown. How do you explain this? The forward reaction of NO2 dimerizing into N2O4 is an exothermic reaction. You have seen that increasing the temperature for an exothermic reaction favors the backward reaction. Hence, the backward reaction of formation of NO2 occurs when the tube is placed in hot water. This is why you see that the brown color intensified in that tube. Lowering the temperature for an exothermic reaction favors the forward reaction. Hence, when the tube is placed in a freezing mixture, the forward reaction of NO2 dimerizing into N2O4 is favored. That is the reason why you see the tube turning pale. Now, let us look at the influence of a catalyst on equilibrium. A catalyst has no effect either on the position of equilibrium or on the equilibrium composition of a reaction mixture. However, a catalyst increases the rate of the reaction by providing a new low-energy pathway for the conversion of the reactants into products. A catalyst lowers the activation energy for the forward as well as the reverse reaction by exactly the same amount, and thus makes it easy for the reaction to proceed faster in either direction. To understand the effect of a catalyst, consider the gas phase reaction of the formation of ammonia from hydrogen and nitrogen. The formation of ammonia is an exothermic reaction and proceeds with a decrease in the number of moles. According to Le Chatelier's principle, the conditions favorable for the formation of ammonia are low temperature, since the forward reaction is exothermic, and high pressure, as the reaction proceeds with a decrease in the number of moles. However, the conditions cannot be maintained because at low temperature, the reaction is so slow that it makes the process uneconomical. High pressure gives a high yield of ammonia, but the higher the pressure, the greater is the cost and maintenance of the equipment. Fritz Haber, a German chemist, discovered that using a catalyst consisting of iron permits lower operating temperatures and a moderate pressure. Thus, the optimum conditions for the industrial method of the synthesis of ammonia by Haber's process are a pressure of 200 atmospheres, a temperature of 725 to 775 Kelvin, and an iron catalyst to speed up the reaction. The importance of a catalyst can also be understood by its use in the manufacture of sulfuric acid by the contact process. One of the important steps in the manufacture of sulfuric acid by the contact process is the formation of sulfur trioxide from sulfur dioxide and oxygen. The forward reaction leading to the formation of sulfur trioxide is an exothermic reaction, involving a decrease in the number of moles. Thus, according to Le Chatelier's principle, low temperature and high pressure favors the formation of sulfur trioxide. However, at low temperature, the reaction is very slow, while at high pressure, the tars used in the synthesis get corroded. Hence, to maintain optimum conditions and increase the rate of the reaction, a catalyst such as platinum or vanadium pentoxide is used. The optimum conditions used for the industrial synthesis of sulfur trioxide are normal pressure, a temperature of 673 Kelvin, and a catalyst such as platinum or vanadium pentoxide. In this image, one beaker contains aqueous sodium chloride solution and the other contains aqueous sugar solution. How will you identify which beaker contains the salt solution and which contains the sugar solution? Obviously, the beaker indicated by the glowing bulb contains the salt solution, and the other beaker, where the bulb is not glowing, contains the sugar solution. Substances like sodium chloride, which conduct electricity in their aqueous solutions, are called electrolytes, and molecular compounds like sugar, which do not conduct electricity, are known as non-electrolytes. This classification of substances into electrolytes and non-electrolytes based on their ability to conduct electricity was made by the English chemist and physicist Michael Faraday. Michael Faraday further classified electrolytes into strong and weak electrolytes. According to him, strong electrolytes undergo dissociation completely when dissolved in water, while weak electrolytes undergo dissociation only to a limited extent. For example, HCl is considered a strong electrolyte as it undergoes dissociation completely when dissolved in water. An aqueous solution of HCl contains only H+ and Cl- ions. On the other hand, acetic acid is considered a weak electrolyte as it undergoes ionization to a very limited extent. An aqueous solution of acetic acid mainly contains unionized acetic acid molecules in equilibrium with the few hydrogen and acetate ions. Hence, the equilibrium involving the ions in an aqueous solution of a weak electrolyte is called ionic equilibrium. Ionic equilibrium can be conveniently studied under two headings: dissociation equilibria, solubility equilibria. Dissociation equilibria. The equilibrium between a dissolved undissociated molecule and its ions is known as dissociation equilibria. In general, dissociation equilibria involve either acids or bases. We deal with many acids, bases and salts in our daily lives. Even some food items contain acids. For example, orange juice and lemon juice contain citric and ascorbic acids. Tamarind paste contains tartaric acid. Curd contains lactic acid. Spinach contains oxalic acid. Salads which are flavored with vinegar contain dilute acetic acid. Isn't it amazing that HCl is produced in our body and helps in digestion? The bases commonly used in our daily life include ammonium hydroxide in cleaning liquids, magnesium hydroxide as an antacid, and sodium hydroxide in the manufacture of soap. Many compounds known to us may be classified as salts. The salt most familiar to all of us is sodium chloride, which forms an important component of our diet. Washing soda used for washing and baking soda, which is used in baking, are also the examples of commonly used salts. The word acid is derived from the Latin word acidus, which means sour. Acids exhibit certain properties in their aqueous solutions. They are sour to taste. They turn blue litmus red. They react with active metals like zinc and liberate hydrogen gas. On the other hand, bases display the following properties in their aqueous solutions. They are bitter in taste. They turn red litmus blue. They are soapy to touch. Arrhenius gave the first real classification of the chemical nature of acids and bases, which is popularly known as Arrhenius theory. According to his theory, an acid is a substance that contains hydrogen and ionizes in an aqueous solution to give hydrogen ions. For example, HCl contains hydrogen and ionizes in water to H+ and Cl- ions. The ionization of hydrochloric acid in an aqueous solution can be represented in the form of equation 1 or equation 2 as shown here. As a bare proton, H+ is very reactive and cannot exist independently in an aqueous solution. Instead, it bonds to an oxygen atom of the water molecule and forms H3O plus the hydronium ion. A base is a substance that contains the hydroxyl group and ionizes in an aqueous solution to give hydroxide ions. For example, NaOH contains a hydroxyl group and ionizes in water to Na+ and OH- ions. The ionization of sodium hydroxide in an aqueous solution may be represented in the form of an equation as shown here. A hydroxyl ion, like H+, also exists in the hydrated form, like H3O2-. Although H+ and OH- exist in the hydrated form, for the sake of simplicity, we usually write H+ and OH- rather than H3O+ and H3O2-. However, the Arrhenius theory of acids and bases has some limitations. It is limited to aqueous solutions only. For example, HCl is considered as an acid only when it is dissolved in water and not in some other solvent such as benzene. Some substances exhibit the properties of a base though they do not contain hydroxide ions. For example, liquid ammonia behaves as a base although it does not contain any hydroxyl group in it. In an attempt to overcome the limitations of the Arrhenius theory, Danish chemist J.N. Bronsted and English chemist T.M. Lowry proposed a more general definition of acids and bases. According to the Bronsted-Lowry theory, an acid is a substance that exhibits a tendency to donate a proton, and a base is a substance that exhibits a tendency to gain a proton. In other words, proton donors are acids and proton acceptors are bases. Consider a generic acid-base reaction. Ha plus water in equilibrium with H3O plus and A minus ions. In the forward reaction, Ha donates proton to water and thus acts as a Bronsted-Lowry acid, while water accepts the proton and acts as a Bronsted-Lowry base. Did you notice that water, which acts as a Bronsted-Lowry base, has turned into a Bronsted-Lowry acid after accepting the proton, and the species Ha, which acts as a Bronsted-Lowry acid, has turned into a Bronsted-Lowry base after donating the proton? This is because a Bronsted-Lowry base, after accepting a proton, becomes a Bronsted-Lowry acid as it has a proton to donate, and a Bronsted-Lowry acid, after donating a proton, becomes a Bronsted-Lowry base as it now has room to accept a proton. The species that remains after an acid gives up its proton is called the conjugate base of that acid. Similarly, when a base accepts a proton, the resulting species is called the conjugate acid of that base. Thus, such a related pair of an acid and a base, which differ by a single proton, is called a conjugate acid-base pair. In the generic example that we saw just now, H3O plus is the conjugate acid of the base, H2O, and A minus is the conjugate base of the acid, HA. Now, in the ionization of HCl in water, HCl acts as a proton donor and water acts as a proton acceptor. Hence, HCl and water are called Bronsted-Lowry acid and base, respectively. As you can see, in the reverse reaction, the H3O plus ion acts as a proton donor and the chloride ion acts as a proton acceptor. Thus, the H3O plus and Cl minus ions act as Bronsted-Lowry acid and base, respectively. Observe that the H3O plus ion, H2O, and the HCl and Cl minus ions differ from each other by a proton only. Therefore, you can say that H3O plus is the conjugate acid of the base H2O, and Cl minus is the conjugate base of the acid HCl. In the dissolution of ammonia in water, the water molecule acts as a proton donor and the ammonia molecule acts as a proton acceptor. Thus, the water and ammonia molecules are called Bronsted-Lowry acid and base, respectively. In the reverse reaction, the ammonium ion NH4 plus donates a proton to the hydroxide ion OH minus. Hence, NH4 plus and OH minus act as Bronsted-Lowry acid and base, respectively. In this case, the OH minus ion is called the conjugate base of the acid H2O, and the NH4 plus ion is called the conjugate acid of the base NH3. However, even this theory had its limitations. The theory fails to explain some reactions that do not involve a proton transfer. For example, the neutralization reaction between the acidic oxide, carbon dioxide, and the basic oxide, calcium oxide, does not involve any transfer of proton. It fails to explain acidic behavior of electron-deficient molecules like AlCl3 and BCl3. In 1929, G.N. Lewis proposed a more general theory of acids and bases, which is founded upon the electronic theory of valency. According to this theory, an acid is any molecule or ion that can accept an electron pair to form a coordinate covalent bond with the donor. For example, H+, BF3, AlCl3 and SnCl4 act as Lewis acids. A base is any molecule or ion that can donate a pair of electrons to form a coordinate covalent bond with the acceptor. For example, NH3, H2O and OH- ion act as Lewis bases. In short, an electron pair donor is a base and an electron pair acceptor is an acid. According to this theory, a neutralization reaction is simply the formation of a coordinate covalent bond between an acid and a base. For example, in the formation of NH3BF3 abduct, the boron of BF3 accepts a lone pair of electrons from the nitrogen of ammonia and forms a coordinate covalent bond. The Lewis theory had its limitations too. This theory fails to explain the strength of acids and bases. All the acid-base reactions do not involve coordinate covalent bond formation. For example, the reaction of HCl with NaOH does not involve any formation of a coordinate covalent bond. Generally, acid-base reactions are very fast, but in certain cases, the formation of a coordinate covalent bond is very slow. Of the two beakers, A and B, one contains hydrochloric acid and the other contains acetic acid. Identify which one contains hydrochloric acid. Beaker A, doesn't it? How do you explain that? Its brightly glowing bulb indicates the ability of the solution to conduct electricity, which, in turn, indicates the presence of a large number of current-carrying particles in the solution. HCl, being a strong electrolyte, undergoes almost 100% dissociation in water. As a result, the solution contains a large number of ions that help conduct electricity to a greater extent. Acetic acid, on the other hand, is a weak electrolyte and undergoes very little ionization. Thus, the solution contains mostly unionized acetic acid molecules. Therefore, very few ions are available to conduct electricity, and so the flow of electric current is weak. Hence, the bulb glows very faintly. According to the Arrhenius theory, the strength of an acid and a base is related to the ease with which they function as a source of H+ ions and OH- ions in an aqueous medium. As hydrochloric acid, sulfuric acid, nitric acid and perchloric acid undergo almost 100% dissociation, they are said to be strong acids. These acids act as proton donors. Similarly, bases such as sodium hydroxide, potassium hydroxide, and cesium hydroxide are also called strong bases as they undergo complete dissociation in an aqueous medium, furnishing OH- ions. In terms of the Bronsted-Lowry theory, a strong acid is one that readily donates the proton, while a strong base is one that readily accepts a proton. The greater the tendency of an acid to donate protons, the stronger it is. Similarly, the higher the tendency of a base to accept protons, the stronger it is. To understand the statement better, consider the ionization of HCl in water. You can see from the equation that Cl- is the conjugate base of HCl and H3O+ is the conjugate acid of the base H2O. Now, as you can see, there are two acids, HCl and H3O+ in the reaction. Now, which one is stronger? Obviously, HCl. This is because HCl shows a greater tendency to lose protons than the H3O+ ion, and hence, the solution primarily contains Cl- and H3O+ ions. Generally, the equilibrium will shift in the direction of weaker acid, and the resultant solution mainly contains Cl- and H3O+ ions. As HCl is a strong acid, it readily loses the proton. Does this tell you anything about the chloride ion as a base? Yes, it does. HCl is a strong acid, which means that every HCl molecule produces H+ and Cl- ions. This further means that the forward reaction predominates in this reaction. In an aqueous solution, there are virtually no HCl molecules, but only H+ and Cl- ions. This shows that the Cl- ion has very little ability to attract the H+ ions in the water, and thus is a very poor base compared to the water molecule. Hence, it follows that a strong acid has a weak conjugate base. Strong acids like hydrochloric acid HCl, sulfuric acid H2SO4, nitric acid HNO3 and perchloric acid HClO4 have a very weak conjugate base like chloride ion Cl- ion, bisulfate ion HSO4- ion, nitrate ion NO3- ion and perchlorate ion ClO4- ion. Now, let's consider the dissociation of acetic acid in water. It is a weak acid. The term weak acid means that it undergoes dissociation to a less extent, and thus, very few ions are present in the solution. This means that the backward reaction predominates in its aqueous solution, and acetic acid remains largely in the undissociated form. This clearly indicates that the acetate ion strongly attracts the protons in the water, and thus it is a strong base compared to the water molecule. Hence, you can infer that a weak acid has a strong conjugate base. Weak acids like acetic acid CH3COOH and hydrofluoric acid HF have very strong conjugate bases like acetate ion CH3COO- ion, fluoride ion F- ion respectively. You might have observed that during acid-base titration reactions, indicators like phenolphthalein and bromothymol blue are used. Generally, indicators are weak organic compounds that exhibit different colors in acidic and basic media. For example, phenolphthalein is colorless in an acidic medium and pink in a basic medium. This change in color helps us in identifying the end product of an acid-base reaction. Observe the two reactions of the dissolution of ammonia in water and the ionization of HCl in water. What do you infer? You can see that water is capable of acting both as an acid as well as a base. Pure water is a poor conductor of electricity. Conductivity measurements show that water ionizes to a very limited extent. This equilibrium constant Kc for this equilibrium can be written as Kc is equal to the product of concentration of H plus ions and concentration of OH minus ions divided by concentration of H2O. Since the ionization of water is negligible, the concentration of water can be taken as constant. Thus, the concentration of H2O can be incorporated in the value of Kc to give a new constant, Kw, called the ionic product of water. The ionic product of water, Kw, at a given temperature, is defined as the product of the concentrations of the H plus and OH minus ions in water or in aqueous solutions. Experimentally, the concentration of H plus ions at a temperature of 298 Kelvin was found to be 1.0 multiplied by 10 to the power of minus 7 moles per liter. The dissociation of water produces equal number of H plus and OH minus ions, and hence the concentration of OH minus would also be equal to 1.0 multiplied by 10 to the power of minus 7 moles per liter. Thus, at 298 Kelvin, the ionic product of water, which is equal to the product of the concentrations of H plus and OH minus ions, is equal to 1 multiplied by 10 to the power of minus 7 raised to the power of 2 moles per liter. This is equal to 1 multiplied by 10 to the power of minus 14. Hence, the value of the ionic product of water at 298 Kelvin is equal to 1 multiplied by 10 to the power of minus 14 moles square per liter square. It must be remembered that Kw, being the equilibrium constant, depends on temperature. The aqueous solutions of various substances can be divided into neutral, acidic or basic, depending upon the relative amount of H plus and OH minus ions. In neutral solutions, the concentration of H plus ions is equal to the concentration of OH minus ions. In acidic solutions, the concentration of H plus ions is greater than the concentration of OH minus ions. While in basic solutions, the concentration of H plus ions is less than OH minus ions. The concentration of hydrogen ions is commonly expressed in terms of the pH scale, which was introduced by S.P.L. Sorensen. The P in pH comes from the German word Potenz, meaning power, and the H from the concentration of H plus ions. The pH of a solution is defined as negative logarithm to the base 10 of the molar hydrogen ion concentration in a solution. Thus, the pH of a solution containing hydrogen ion concentration of 10 to the power of -4 molar will be equal to 4. You have seen that at 298 Kelvin, the concentration of hydrogen ions in pure water is equal to 10 to the power of -7 moles per liter. Thus, the pH of pure water is 7. Thus, for neutral solutions, the H plus ion concentration is equal to the OH minus ion concentration, and the pH is equal to 7. For acidic solutions, the H plus ion concentration is greater than the OH minus ion concentration, and the pH is less than 7. For basic solutions, the H plus ion concentration is less than the OH minus ion concentration, and the pH is greater than 7. The pH of some common substances is shown here. The pH of a solution can be roughly estimated using a pH paper that gives different colors in solutions of different pH values. For accurate measurement, pH meters are used instead of pH papers. A pH meter is an electronic instrument that measures the pH-dependent electrical potential of the test solution. As we saw earlier, the ionic product of water at 298 Kelvin is equal to the product of the concentration of H plus and OH minus ions, which is equal to 1 multiplied by 10 to the power of -14. On taking negative logarithm on both the sides of the equation, we get negative log of Kw is equal to negative log of H plus and OH minus ion concentrations, which is equal to negative log of 1 multiplied by 10 to the power of -14. Negative log of H plus and OH minus ion concentrations can further be written as negative log H plus ion concentration and negative log of OH minus ion concentration. This is equal to negative log of 10 to the power of -14. As negative log of Kw is equal to pKw, negative log of H plus ion is equal to pH, and negative log of OH minus ion concentration is equal to pOH. Thus, the ionic product of water at 298 Kelvin, pKw, is equal to pH plus pOH, which is equal to 14. Based on the pKw value, the pH scale has markings from 1 to 14, and the nature of a solution as neutral, basic or acidic is determined depending on its value on this scale.